I'm going to put a positive charge right here in this uniform electric field, and I'm going to let go. The charge flows toward the negative because of attraction. This charge just lost potential energy as it flowed with the field lines. And the change in potential energy per Coulomb is called potential difference. Energy cannot just be created or destroyed, so this potential energy has to go somewhere. What does it turn into? As the charge flows through the field, it feels a net Coulomb force. And Newton's second law says net forces produce acceleration. The charge speeds up. So as the charge speeds up, the energy turns into kinetic. The charge loses potential energy, so the delta is negative, and it gains kinetic energy, so that delta is positive. But delta PE, if we cross multiply, is Q times the potential difference. The change in kinetic is final minus initial, and we'll assume it starts at rest. This equation is useful when solving problems. The little v, lowercase, is speed. Capital V is potential difference. In the picture above, this is a vacuum in between the plates. There are no other charges, no other particles. It's empty. But if you take your toaster and you connect your toaster to a battery, here's the toast, here's the battery, the same kind of thing happens. Charges spill out of the battery and flow through the toaster. But when those charges reach the toaster, it's not a vacuum. The toaster has molecules that the charge has to flow by. And when the charge flows, it bumps into those molecules. Each collision transfers energy to the molecules, and the molecules move faster. That random molecular movement is temperature. So in this scenario, we convert the potential energy into heat, which is transferred to the toaster. When we do this, there are a couple of ways it might look. Now, when I drew my picture above with the battery, I was being inaccurate. A battery is not a single charge. A battery is like a bucket of charges that we let spill out. When we tip over the bucket of charges, will they flow at a high rate or a low rate on top? What about on bottom? On the top picture, fewer charges pass per second, and they go slower. On the bottom, more charges flow per second, and they go faster. Current, I, measures how quickly charges flow through a device. It's the rate at which charge flows. And we show that with this equation. If we mark a line and we count how many charges flow by per second, then now we're measuring current. What's another difference between the two pictures? There's more opposition here and less opposition here. Resistance measures how much opposition there is to the flow of charge. On top, we put potential difference, and in the definition of resistance, we divide by current. The unit for current is the Coulomb per second, and we define that as an ampere. The unit for resistance is going to be potential difference, that's volts, over current, that's in amperes, and we define that as an ohm, which is sort of like a U, an upside down U with feet. This is the Greek letter omega, by the way. Batteries are devices that separate charges across the terminals. If the battery doesn't separate many charges, it doesn't have a lot of energy or potential difference to offer. Batteries that separate lots of charges have more potential energy or more potential difference. So if we connect a single device to all three batteries, where does more current flow? We can use the definition of resistance to answer the question. Let's assume that the resistance R is constant for the device. If we write a proportionality, R goes away because it's a constant. And if we rearrange, we get this. Increasing the potential difference causes current to increase. So more current spills out of the bigger battery. If we make a plot with the different battery voltages or potential differences and current, what kind of graph do we get? The graph of a direct proportionality. This is called Ohm's law. Ohm's law states the resistance of a device is fixed at a wide range of potential differences if temperature stays constant. Devices that follow Ohm's law, devices with fixed resistance, are called ohmic. Not all devices follow this law, only some have a fixed resistance. Let's summarize what we've learned and make an outline. If charges accelerate across a vacuum, their potential energy is converted to kinetic energy. The potential energy is equal to Q times the potential difference, and the change in kinetic energy is 1/2 mvf squared if we start from rest. Finally, the object accelerates because it feels a net force, and the net force that it feels is the Coulomb force. In an electrical device, the energy change is different. Instead of converting potential to kinetic, we convert potential into heat that's transferred to the device. We define the current through the device as the rate at which charge flows, and the unit is the ampere. We define the resistance of the device as the potential difference, V, across the device, divided by the current, I, through the device. We use ohms to measure resistance. Finally, we learned Ohm's law, which states that the resistance of a device is constant at many different values of potential difference, provided that the temperature stays fixed. Ohm's law says resistance is a constant, so potential difference V is directly proportional to current. And finally, we learned that this is only true for some devices, and those devices we call ohmic.